Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 24, 2025, just yesterday. The Hook is a generative physics network called PhysCtrl that drives image-to-video models with physically plausible 3D point trajectories, hitting VIOU 77.03% and winning user preference for physics plausibility at 81.0%. The paper is titled PhysCtrl, Generative Physics for Controllable and Physics-Grounded Video Generation. And as we will see later, the results are really impressive. Beyond that, the method learns across 4 materials from 550,000 simulations, uses spatiotemporal attention and physics losses to enforce realism, supports force and parameter control, and even estimates material stiffness in about 2 minutes. Figure 1 shows how PhysCtrl turns a single image and a force cue into controllable, physics-grounded motion in video. The colored dot clouds represent 3D point trajectories, which are moving samples on the object that trace its path over time. The grid demonstrates material control across 4 types, and it also varies Young's modulus E to make the same object deform more or less. The bottom row illustrates force control, so the plane responds differently when the push direction changes. Well, Figure 2 shows the full pipeline, which connects point cloud lifting, trajectory generation, and video synthesis. The left panel converts a single image into a 3D point cloud that can drive motion. The middle panel predicts point trajectories using a conditional diffusion model controlled by physics parameters and a force, where a drag point means the location where the push is applied. The right panel turns those trajectories into a video using a pre-trained generator. Alright, Figure 3 explains the trajectory generator, which predicts point motions by first mixing information across nearby points and then enforcing consistency over time. The top strip shows conditioning tokens for force, drag point, material, and physics parameters. The middle panel runs spatial multi-head attention with adaptive LayerNorm, which means the features get scaled by those conditions. The lower panel applies temporal multi-head attention. A final layer outputs denoised point clouds. Alright, Table 2 reports quantitative results on trajectory generation. Volume intersection over union means how much the predicted 3D shape overlaps the ground truth shape. Chamfer distance measures the average closest point gap between 2 point clouds, so lower is better. PhysCtrl reaches VIOU about 77%. The chamfer distance is about 0.003. The correlation error is around 0.0016, which beats MDM and Motion 2-volt sets by clear margins. So Table 1 summarizes video evaluation on 3 criteria: semantic adherence, physical common sense, and video quality. PhysCtrl scores about 4.5 on semantic adherence. It also reaches about 4.5 on physical common sense, which signals motions that align with the applied force and position. Video quality comes in around 4.3. The other methods trail noticeably because they rely on text or sparse 2-dimensional cues rather than physics-grounded 3-dimensional trajectories. Wrapping up, 2 takeaways stand out. Learning a generative physics prior over 3D trajectories gives precise force and material control, and the spatiotemporal attention plus physics losses make motions both realistic and robust. The broader implication is faster, simulator-free video control that could power creative tools and lightweight parameter estimation. Thanks for listening. I am Alex, and this was the AI Research Roundup.